11 a.m. Eastern Standard Time here. So this is module 6. And the presenter doesn't need any further introduction. If you are here with us from the beginning, you've met Professor Prem, Professor Sagar. He's a professor at University of Maryland. And then one aspect I'm very interested in, he is also the chief data scientist for Crypto Corporation. The first time he was here, Bitcoin was 50,000. Now Bitcoin is over 60,000. So maybe we have to invite him another time so we can know about all this crypto universe. If today is your first time at the recordings of the past modules, you find that I believe in VADSTI GitHub. If that is not right, Nana can tell us. And then I believe you can also find that under the VADSTI Slack. So without any further ado, let's welcome Professor Sagar again. Again, I tell you, I want to see your faces, but you're always hiding behind the curtains. Just turn your cameras on and then let's wave and welcome Professor Sagar.
Thanks,
okay,
everybody.
Prem, it's all yours.
Hi, everybody. Nice to see all your faces. Thank you for the warm welcome. I hope everybody's doing great. We've got a lot to cover. So today we'll walk through a little bit of a review of, what is, so to talk about classification models, we have to talk about what is machine learning, right? So we'll talk a little bit about that. And then we'll talk about the types of machine learning, how certain types of machine learning apply to classification models. I'll take you through some examples. And I'll also talk to you about how we do this at scale, right? And we'll walk through some examples of that. So by now, you all have been introduced to decision trees. You've seen some neural networks. These are examples of classification models. So I'm curious, has anybody, or does anybody currently now work with classification models in the audience? Is anybody actually doing this work in the field right now? No? Okay. Yeah, okay, well, William, okay, good. Is anybody doing it, is anybody dealing with big data right now? Yeah? Can you elaborate on that, Stephanie? Sure. Just interrupt me whenever you're ready. Yeah. I don't hear you, but I think you show up muted, so you've got to do, yeah. I think, am I able to unmute you? I can't unmute you. So you're muted? Okay. Yeah.
Nana and Stacy, yeah, if you can help.
Yeah.
Yeah, she's going to do that. She can just click on mute.
Oh, okay.
While we're waiting, I could say one word or two, if that's okay.
Sure, go ahead.
So I don't know exactly what big data is anymore or big data are in terms of scale, because I used to think 100,000 cases for big data. So I don't know what classifies as big data anymore, since you can do terabytes and all this kind of stuff. But I work with school data, like statewide kind of longitudinal data. So I'm really excited for this because I have a data set that's clean that I would like to do some classification models with using I have multiple measures of schools sort of nested in districts. So I'm interested in how sort of these sort of nested models are used in classification. So just excited to hear what you have to offer, and hopefully I'll start analyzing this data set today after this meeting. So we'll see.
Yeah, that's great, Candace. So let me see. Stephanie, are you still muted? You look like you're still muted, yeah. And Stephanie, there's a little mute button on the bottom left of your screen. Do you see that? on the WebEx panels. Yeah, and you've tried to unmute that. It's still not doing anything. Okay, Nana will work some magic, and then you can interrupt us later on. So, okay, so it's very much like physics, right? So there are certain, when the data is small or manageable, basic techniques work. We can use pandas. You can use sklearn, no problem, right? And you get all this beautiful visualization that comes out very easily. But when things grow to large proportions and we start talking about big data, and I'll define it for you, right? We're going to see examples of it. We'll get into exactly what it is. You have to change the way you do business. And so we'll get into that as well, right? We'll see how you actually deal with classification models when you have to deal with scale, right? And more often than not, you will have to if you're working on something fundamentally new, right? That hasn't been discovered yet. And organizations and research institutions are always looking at this. Advertising being the biggest. Where are the psychologists in the room? Okay, so we'll get into this. There's a fascinating paper that was, a news piece that was written by the New York Times that talked about how the folks over at Target were using psychology and mice experiments to figure out how to not only what engage with you, but how to manipulate what you want, right? So there's one thing to say, okay, and this is because of big data, right? If we get enough information about you, right, we can predict with high confidence what it is that you want, okay? But what I'm telling you now is the data has been weaponized, that it's not so much telling you what you want, we can make you want something, right? So, if you start seeing a bunch of advertisements, even in the background, I've learned a lot about this recently, right? And it really troubles me. So if there's a bunch of advertisements that are flashing by you, and let's say they're fast food advertisements, which are positively seductive, right? So all of a sudden, you're going to start to feel hungry, right? It's not because you were hungry, right? They have set these things up in front of test audiences to say, if we do this, there's going to be this kind of response, right? And so the field and advertising has used big data and used classifications, buy or not buy, right? They're predicting whether you will buy or you will have a transaction or not. And they've incorporated psychology so that they can, again, not only know what you're going to do, but make you do something, right? So I'll give you one more piece on that, and then we'll get to the slides. There's a statistic that
she's back now.
Go ahead. Oh, Stephanie, are you able? Go, Stephanie.
Yeah, for some reason, all my controls froze up and I couldn't do anything. But yeah, I'm a clinical psychologist, and one of my frustrations about my field is that we have not used that power for good. There are some ways that we could manipulate choice. Why not manipulate choice to help people not shoot, right? Or to eat more healthily. We are working on that. But where I am at the University of New Mexico, I have 2 large data sets right now that we're just starting to scrub. And I'm using the assistance of our analytic team on campus. I'm not by nature a statistician or a coder, which is why I'm in this class, but I'm very fascinated by all the data that we've collected over the years in our EHR. But the 2 major data sets, and that question that came up about what constitutes a truly large data set, for us, we have a data set of about 1,000 individuals with about 70 variables each from a pandemic assessment that we constructed early last year at the start of the pandemic, looking at our entire campus coping with the pandemic, as well as developed what we're calling a cumulative impact scale. So we're doing some analysis on that. We're just starting to scrub that data on the 1,000 participants. And then we've been collecting data on all student deaths since 2004 and have received OMI reports and pulled variables from OMI reports on everything from demographics to what they were studying, to where they were from, to substances, to methods. And we're scrubbing that data now and going to start analyzing that this summer. But that's the one where we have hopes to improve the predictive models for suicide, which has been, you know, the elusive task in the field of psychology forever. And so that's what we're hoping to be able to do.
Fascinating. So thanks for sharing that, Stephanie. And let me just ask, you know, in your professional opinion, advertising is largely able to manipulate the public. Yeah.
I'm just surprised about how we don't use it. You know, in my opinion, we could have been applying it, you know, pretty effectively to avert, you know, the past few years of terrible foreign policy. You know, we could have been doing a lot of things, right, to help our public, you know, be more humanistic. We could be using it for those purposes, but we tend not to. You know, I'm always surprised about how we're not applying what we can do more so than what we do apply. Yeah.
No, it's very fascinating. So, in many ways, you are in the matrix.
Yes.
Right? And you think that's air you're breathing? I mean, there are forces at work that are dictating what you do and what you like. Right. And that has been in a large degree brought on by big data, specifically advertising, right? Like, so have I told you all the Target story?
Mm-hmm.
Yeah. Okay. And that's a situation, right? So the question is, you know, is it that they knew that she was pregnant, or is it that they advertised in a way, or there's some advertising going on to have caused her to go get pregnant, right? Like, where does the chain start, right? And I don't know how nefarious that is, right? But these things are, in psychology in particular, right? I find it very fascinating because when you look at other phenomena like the stock market, you know, at even monthly terms, hard to predict, right? Long term, maybe. But psychological behavior for masses is pretty predictable, you'd say, Stephanie, or?
Well, I don't know if it's pretty predictable. We've not utilized in our field because we're, you know, there's a huge research contingent, but it tends to be, you know, our research powerhouses tend to be focused on, you know, brain functioning and direct clinical service and treatment models. And I'm not sure, I'm not really aware of how we've been using it, you know, with this mass sort of public application. You know, I'm always surprised why, you know, for example, political parties aren't, you know, more commonly utilizing what we know in data science and in psychology to kind of influence the masses. I'm wondering, where is that happening? And it doesn't seem to be, but you know, so I say that I don't see any evidence that that's happening.
Yeah, I agree with you. Okay, and is anybody else in the audience dealing with big data? We're going to get into exactly what this is. Let me share my screen out as we go. So
when you talk about classification, is it the same as, let's say, you watch a couple of YouTube videos, or then later you see that similar videos like that follow you anytime you log onto a computer, different, even your phone, they tag you with similar videos. Is
Yeah.
it like does it fall in that category?
So it's systematic advertising, Nana, right? So what's happened is this is a phenomena based on cookies, right? And the idea is, it's interesting why it happens though, okay? So it does fall into classification. They are trying to target you as a buyer, right? And they think that these factors of advertising are going to get you to do something, right? But what's really fascinating about this is 40 to 50% of your brain function is habitual. You're not really making the decisions like consciously, Nana, right? So, the way we're breathing right now, my tone, right? All these things are sort of happening, okay? Now, me thinking about your question is the brain spinning round and round, right? So what happens with this advertising, specifically on the internet, is, let's say, you go to Amazon and you look at something and then you move off and all of a sudden you go to another web page and these ads appear and you see it. Okay, great. Bonus. All right. And you recognize that you've seen it. Bonus. All right. But Nana, what I'm telling you is, even if you don't consciously see it, right, your mind took a picture. Right. And what's happening is, even though you may not have even known that was there, the fact that it flashes on your screen, your brain has that somewhere, right? And what's happening is, if you see it enough times, Nana, right, it's like you saw it and you were consciously looking at it. You see, nobody clicks on ads. We know this. So this idea that click on an ad, it's going to generate money, it's propaganda, right? The ads are there to subliminally get you to do things, to suggest this to your subconscious, Nana, right? And that is why, this is just me now, okay? That is why I only pay for services when I can afford it, right? So like my email, I try to make sure that it's paid for because I don't want the programming to come down. Because even if I'm not going to look at it, my brain is still registering, Nana, right? You see it, you're just not consciously thinking about it. So it is there, and you should know that it is. I mean, I have ethical issues with this stuff, right? And so, and you have to think, like, we have obesity problems. You don't think that's a function of advertising?
It is.
Yeah, right. Absolutely, right? And so, these things need to be dealt with at high rank because, there's profound impact because of that, right? So, so it is classification, Nana. They know what you want. They know how to target you. And they know that this amount of advertising is going to be effective or not, right? They have paid campaigns for this. I'm not saying that industry is bad, right? Like, I'm in industry, okay? And I'm not saying that profit is bad, but I'm saying that there have to be ethical limits to where you go, right? And I don't like the subliminal advertising thing. I think it's strange, especially, I don't know how many of you, those of you in the audience who have children who are certainly using devices now because we can't go anywhere, all right? And so you have these apps, and the apps have these ads, and to children, that is like magnetism, right? You're basically putting it into their mind. They don't have anything else in there to fight it off. So, there really shouldn't be advertising for these kids at all because, this is making up their psyche now, right? So if you take anything away from today, right, take away that advertising controls masses, and you should be cognizant of it, right? And that they use classification models in advertising to control what you do. Not know what you do, control what you do. Pay for services. Get out of the matrix, all right?
Yes.
Okay. All right. So, all right. Can everybody see my screen? Yeah? Good?
Yeah. Good.
So, brief recap, right? So we have artificial intelligence, that's sort of the broad spectrum of what's going on here, right? Being able to use machines to look at data and come up with answers, right? So similar to how a human being would do it, right? So there are certain machines certain technologies that can do that. We'll talk about Mitsuku. Is anybody familiar with Mitsuku? Okay, so you'll find that there are like three big problems, right? There's classification, there's regression, and then there's clustering. These are like three big ones that we look at, right? And even so Mitsuko is a chatbot who won the Loebner Prize for being as close to a human being as possible. I'll show you some slides on that as well. And what chatbots do is they read in what you've given them as data. So that's the X input, right? And then they have a classification engine that says this is what the output should be to be satisfactory, right? So much of this boils down to classification models. And machine learning, there's really two types now, right? So classic machine learning, the idea is that it learns from the data as opposed to the programmer, right? I'll draw a lot of this for you so it crystallizes. And then there's deep learning, right? Deep learning works for clustering, deep learning works for regression, and deep learning works for classification models. And we'll get more into this as we go as well. And the idea here is forget trying to get it right at the beginning. Let's just do trial and error until it gets it right, right? And we're willing, and I'll draw some examples of this as well. We'll see an example of where a traditional machine learning attack for a classification model would benefit from going to deep learning, right? Okay, so very quickly, so everybody remembers unsupervised versus supervised, all right? So for classification models, all right, the vast amount of classification models are supervised learning, right? There is a subset of this which is used for anomaly detection, okay? And the reason I'll talk about anomaly detection in a second, but the reason the classification models are supervised learning is currently, right? And like every time I give this brief, I feel like we're that much closer to it not being the case. Currently, the machines need us to say what something is outside of like simple images, right? So there's a lot of work that's gone into image detection so they can figure out that this is a dog, this is a cat, etc., right? But if you want to say that something is good or bad, or something more specific to your organization, like this is a suicide case, this is not a suicide case, right? They've not built up those classification models yet, right? And even the models that are doing it on images have been initially trained by humans, right? Humans were in there saying, this is an example of a bicycle. This is an example of a tree, right? And all this stuff was coded for the machines. The machines looked at the patterns of the images and said, oh, when I see these patterns, it turns out to be a tree. And when I see these patterns, it turns out to be a bicycle, right? So, and then what happened is they packaged that up. They call those convolutional neural networks. It's really just image detection that's been done for you, so you don't have to do all that training, and they've given you a classification model for it, right? But for specific reasons for your organizations, it's mostly done through supervised learning. Now, the specialized case of it, let's see if I can draw here. The specialized case of it is for anomaly detection, right? And in that situation, let's say you have, I'm trying to draw here, but I don't think, let me see this. Draw, let's go to, yeah, that's the problem, I was in black. Let's do green, okay. All right, so in anomaly detection, there's you can do some things because of the math of the situation, right? So let's say you have some data that looks like this, okay? And so a scatter plot. And what we can do in these situations is we can identify clusters. Maybe this is one grouping, okay? And we can identify clusters in unsupervised. Let me try to draw this. I'm just going to put U for short, right? We can get clusters in unsupervised, all right? And then what you can do is you can find the clusters with the rarest amount or least, let's say entities, right? Entities. All right. And then you can say, okay, look, this is an anomaly. All right, we can check this guy off. All right, so this is a special case where we can try to say that something is more rare, right? And this basically comes down to the fact that a number is either less than, equal to, or greater than something, right? So you have this basic classification sort of built into the mathematics of the situation, right? We can say that, you know, A is less than B. We can say that maybe A equals B, and we can say that maybe A is greater than B in certain circumstances. And then we can look for things that are less than everything, right? And target those things as anomalies. And the latest versions of this can be done unsupervised, right? So, okay, today we'll talk about classification models that, give me a second, let me just close my door. Okay. So today we'll talk about supervised learning classification models, but if you have questions about the unsupervised side of this, I'm happy to entertain that as well. Okay, so, you know, an example of this, and then we'll get to Jupyter so you can actually see things running. Here's an image, right? We're trying to figure out if it's a cat or a dog. And this is an example using a neural network, right? So we basically, this first grid down here are the pixels, right? And we analyze it, and then we say, because we've trained this thing before, we've given it, you know, thousands, maybe millions of pictures of cats and dogs. It looks at the patterns in here and it says, oh, this, you know, there's a signal coming through on maybe this neuron, right? Which is, you know, some node in a graph for this neural network, and it fires. Very much like how things work in the brain, right? Like you see something, and if the signal is high enough, let's say it's something that makes you afraid. Let's say you hear a noise that's very loud, right? So that will target some neurons in your brain. There's a signal coming through, and that sets off a chain reaction of, okay, now we need to be afraid, right? So same thing here. The machine sees some pixels. The pixels, you know, will have a strength. That strength will be sent to one of these neurons. If the strength is strong enough, the neuron will fire, right? And then propagate that information on. And what happens is we start to filter as we go, right? And we ultimately end up by taking all these pixels and minimizing that down to a decision of either cat or dog. It's a big simplification. You guys just went through neural networks, but this is the idea, right, behind it. And the reason we call it deep is because it's multiple stages, right? And why does this work? Somebody from the audience, because you guys just went through this, right? Why do neural networks work? What did you guys get out of the last lecture? What is the big oomph in them? So the big thing is the back propagation. The ability to correct it is what does it. And I'll talk about that. I'll give you some examples of why that is the case and where it differs from a classic approach, right? Okay, so, all right, so that's deep learning. We've seen this. This is the decision tree from before on whether or not we were going to get a big tip, right? And this takes an entirely different approach, right? Like, we won't go through the intricacies of all of this, but because you guys will have seen this before, but the point is the decision tree looks at, you know, this data, okay, and says, you know, what are the patterns within here? And all of this happens, very interesting. And you'll see this, there's something called schema on read and schema on write. Anybody heard this before? Yeah? Okay. So this is, we talk about this in big data. right? Big data. But there's a parallel to it in machine learning. There is train on read, right? And train on write. Okay? So what happens is when you are working with decision trees, anything really outside of neural networks, you're training on the right. Okay, and what that means is the model has to be like the features, these variables that you have to be just about perfect for the machine to understand what's going on. Right? I only have, let's say, 5 minutes with someone to teach them algebra. Right? How am I going to do that? I don't have the ability to teach them over time. So when I get in there and I'm trying to teach this person algebra, it has to be perfect. Right? It's got to be completely visual. There have to be variables falling from the sky. The light bulbs have to go up. All this has to be there. Okay. So that is very much how traditional machine learning works. Traditional classification models work this way. It's got to be almost perfect. All right. Now, with neural networks, you don't spend that much time at all. You're training on the reads of the situation. So there we say, okay, I have a year to teach you algebra, okay? And I'm going to continue to give you examples and examples and examples over and over and over again. And eventually, your mind will understand what algebra is. And it doesn't have to be great. It can be pretty bad. But we're just going to keep trying and trying and trying and trying and trying, right? So that is another attack. And that works because we now have the processing power to run these things over and over and over again on big data sets, right? So, and before we did not, right? The technology was just not there for it, and the processing power was not there. But trial and error, until we figure out the partial differential equations that govern everything, okay? Trial and error seems to be the way to go forward. So, okay. So now let's talk a bit about big data. If anybody in the audience knows this, that's fine, right? I always ask this thing, is it dangerous? So the question came up before, well, what is big? Good question, right? Big is a relative term, okay? And it's assumed to be big by today's standards. However, what it really means is it's too big for you to handle via vertical scaling, all right? This is the thing. So there's two kinds of ways to improve your computing horsepower. Two ways to do this. The first way, which is the way that we have been doing it for a long time, is vertical scaling, all right? So that effectively is you have a computer and things are too slow, so you either increase the RAM in the computer or you increase the hard disk, or maybe you get a whole new computer and port the data over, right? And that's typically what happens in organizations, right? We go through these refreshes, everything is faster now, fantastic, okay? But there's some problems that are so big in multiple facets that you doing that, it's not going to really move the needle, okay? So how do you get around that, okay? The other way to do this is something called horizontal scaling, right? And what that means is rather than you going out and getting a whole bunch of new hardware, improving your computers or buying more, you would effectively farm out some of the job to other people, right? You take that, let's say the problem is size. You take that gigantic data set, and rather than you processing it on your set of machines, you give maybe half to some other, people to process, okay? So now I know what you're thinking. How do you synchronize all that, right? How do I keep track of what I gave, to this person over here, or this machine over here, and this machine over here, and run these operations, right? And that problem is solved by distributed computing and really two lead frameworks, both of which you will see today. One, which is Spark. Anybody using Spark in the audience? No, okay, yeah. And the other one is Dask. Anybody using Dask in the audience? Yeah. Okay. William is very. William, do you prefer Spark or Dask? You're muted, so I can't hear you. Yeah. You can if you.
Now, I do a presentation on that for my user, the Python group. So I tried both, but I prefer Spark to Dask.
Okay.
And it's just personal preference primarily.
Yeah.
It's just my personal preference.
Cool. They both have pluses and minuses, right? They're both able to break data sets up, and they're both like the lead technologies to do this. So to give you an example, before there was Spark, there was Hadoop, okay? And Hadoop is what makes most of big tech go, right? Google largely developed Hadoop, right? They knew that they could not keep the entire world's data, all right, on big machines. So they created, they got cheap Linux servers, and they got, millions of them, thousands now, right? And so, and they said, we have to find a way to store all this data. It's too big for any one span or whatever. So they invented a way to have all this synchronization happen and build this file system that looks like it's one file system, but it's actually everywhere, right? They built this facade. And that facade, that API of distributed computing on lots of little boxes grew into Hadoop, okay? And so the world is getting indexed on this stuff. Facebook uses Hadoop. Google uses Hadoop. Researchers use Hadoop, okay? And Hadoop is great, but you have to be basically a Hadoop scientist to be able to do Hadoop, right? It's very, very tricky. It talks about maps and reducing, and the APIs were largely in Java, so you had to be a pretty good Java programmer, and even Java programmers had problems with it. And it was slow to some degree because you had to read everything in, and Hadoop was designed to work at the file system, right? Hadoop is like these big chores that happen in the background, and they run off of disk. Okay, so Spark came along and was very smart. They said, we have access to more memory now. Memory's become cheaper, right? So is there a way for us to pull some of these Hadoop processes into memory, right, to go that much faster? And that which we can't use in memory, let's push it back to disk, right? And so they figured out how to do that. And then they said, no one wants to write MapReduce. Like, trust me, nobody wants to write MapReduce, okay? So what they did is they came up with a SQL interface, and lots of people know SQL, right, for dealing with data. And that is how Spark kind of won the war, right? It built on Hadoop, and it provided a much simpler interface, and it provided extremely fast results when possible by leveraging RAM. I mean, there are some servers, I have worked on servers with a terabyte of RAM in them. It's like you would never, 5 years ago, I'd have said, what are you talking about? It's not possible, right? So, so in processing in memory has become very, very advantageous. Dask is just like Spark, but it's built for Python, right? You'll see the Dask example today, okay, with a classification model. And Dask takes the route of simplicity. It doesn't try to be distributed computing for every language. It is just for Python, at least right now, and it is wildly simple. Once you get past the initial curve of it, Dask is basically Pandas and Python, and is really quite beautiful. And I think that Dask is going to sort of run away with it because so many people are coding in Python. And the idea is, if you have, this is the big thing that Dask did. If you have an infrastructure that's built on Python and Pandas, which a lot of us do, right? And if you don't, it's pretty quick to get there. you can move that infrastructure to DAS basically uninvasively, right? It's a very, very clean switch. And, you know, both these technologies, Spark and DAS, are examples of horizontal scaling, right? So, you know, to sort of tidy up on it, the example is, you know, you have to move a whole bunch of people from, this is from Delhi to Noida at some time, but there's only one bus with a capacity of 25 passengers. So what do? Do we build a bigger bus, or do we go out and get more buses, right? And more often than not, having multiples solves the problem, right? So, okay, so, but what does that mean in relation to big data, right? The point here is the moment you can't solve the problem with vertical scaling, you are now in the realm of big data, right? And it depends on your organization. Let's say that your organization only has a server, like, where was it? So Kenneth, right? So Kenneth is, you know, at an organization, and let's say that he has access to a server that has 30 gig on it in memory, okay? And he's got a terabyte of disk to play with, all right? The moment Kenneth has a data set that is beyond 30 gig, right? And he can't also afford to wait for paging to disk, right? Because he could put the 30 gig in memory, he'd be out then, really, let's say 25, because the OS has to run. So he could put a large portion of the data into memory, and then he could start paging to disk. And he'll eventually get there, right? But it may not meet time constraints, okay? So the moment that happens, Kenneth's got to find a way to solve the problem, right? And in this situation, if you can farm it out, and most things can be farmed out, he would horizontally scale, and he would start using big data libraries like Spark and VADSTI, right? So another example is he's got 30 gig of memory, he's got a terabyte of disk, but the data set is a terabyte and 31 gig large, right? Right away, Kenneth is out of business. He cannot do it on his machine, right? So he's got to farm it out amongst a bunch of machines, and he's going horizontal here, right? And so now, Kenneth, if the university was willing to fund it and give you more hardware or like improve your hardware, you could vertically scale, okay? And I can tell you that if you can manage it by vertically scaling, great. It simplifies something. Not too much, but it simplifies something, right? But chances, well, we know that data is growing, right? And it's very probable that at some point the data will escape your ability to vertically scale. You may already be there, right? So it's better to move horizontally than it is vertically, right? And you can, you know, because the other part of this that is not talked about is communications have become that much faster. Before, imagine we were back in dial-up and you have to send these messages across machines, right? It would not be productive. Right? Some of you may not know what dial-up is. Okay, so I was in the realm of dial-up. All right, so let's just say it's slow, like sending pigeons across, you know, the farm or whatever. Okay, so if that was the case, this would not work. But communications have become so fast that it's much easier now, or conducive to have machines in different places, farming out loads, communicating back with each other. Okay. So at a high level, right, that is what it is. Okay. You cannot manage it on a single machine. It needs to be spread out amongst multiple machines. It's too big, and we'll talk about various facets of it. So we're going to have to horizontally scale. Okay. Each organization will have different views for it. For me, big data is like more than 16 gig in RAM and more than a terabyte on disk. That is not what it's going to be for the University of Maryland or New Mexico or wherever, right? There are much more resources. Okay. But I will have to go horizontal once I cross those limits. Okay. So a little bit more, there's several V's, right? But technically, the community agrees on about 4 of them, and they are volume, All right, so how is your system going to deal with storage as data approaches infinity? In the case with Kenneth is going to add more servers horizontally. Right? We'll get to that bridge when it comes, but as of right now, I need this many servers to do the job. And as we get more users and there's more data, we'll just continue to add servers. Right? Okay. So, and then there's velocity. How will your system deal with fast responses as requests approach infinity? All right. So this is usually related, but it can be unrelated. Kenneth, I'm going to use you because it's a tangible example, right? So Kenneth builds a model, right, for the student information he has, right? He puts it up, and great, John and William go look at it. They say it's fantastic. This is great. We need to get it everywhere, all right? And all of a sudden, the internet starts going to Kenneth's server, okay? So how is he going to manage to get the response times back quickly as the amount of responses, approach infinity, effectively infinity, right? So it's the same thing here. It's done. Sometimes you can get away with using load balancers, but for all practical purposes, we break the data up again, right, onto multiple machines, and we have certain users go here, certain users go there, and we create multiple copies of it, and certain users go here, certain users go there. Right, but the idea is you again have to horizontally scale because there's no machine that can handle the entire world's traffic, right? So you can have big data problems that are with volume. You can have big data problems that are with velocity. This usually comes after you have cracked the volume issue, right? You've got something great. You've looked at big data. You've got a result. Okay, everybody wants it. Okay, now I got velocity issues, all right? And then after that, and this can come actually before volume and after. You'll have variety issues. Kenneth, how many databases are you dealing with right now? You have a couple of sources, or?
I have, one state database and one national.
Okay.
But they're basically 5 subsets of data that I'm sort of putting together, that I put together.
Okay.
Like, for example, I have like student mobility, I have teacher and student retention, or teacher retention. I have another data set that are the ratings that I'm trying to classify for the different schools. And what else do I have? I have the specialty school, whether or not it's like a charter versus something. So you have all these different classifications of specialty schools, whether or not it's a Title I school versus not, if it's a Title I school with no program. So it's all these sort of nuanced things. And then I have, I think that's it. I said the staff, the specialty schools. Oh, and also the directory information as well, sort of like the latitude, longitudinal kind of stuff.
So, Kenneth, how often does the data format change, or is it pretty fixed for you?
It's pretty, really once a year. So these data change once a year. It's not like we have multiple measurements within a single year.
Okay. So Kenneth is lucky in that regard, but if you were building, let's say, an advertising system, you would be constantly feeding in different data sources to enrich the model, demographic information, advertising information, spending information, political information, right? And these formats change. And, the old way of doing this was we would take, and this is back to that, this is where we talk about it. So this is that schema on read versus schema on write, okay? And so the old way is you had source, 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 and you had, let's say, this database, okay? And then everybody is, running reports from here. Reports, searches, etc. Okay? Let me draw this a little nicer. Okay, so the report, searches from here. Okay, and these guys are all coming in over here. And what happens is you have to get, the format, okay, here is definitely going to be different than the format let's say, call this I, N, sorry, format N here. So the formats will differ, okay? And as the amount of sources you have goes up, the formats will most likely differ even more. So how do you deal with that when you have all these sources? And in the old way of doing this, right? So this is schema on write. Okay, that's what we'll talk about here. There is a section over here called ETL. Sorry, this pen is a little bit loose. ETL. Are there any ETL folks in the room? You're all very lucky. ETL is inherently boring and omnipresent and never ending, right? Because if you need a certain field that's not coming through all these transformations, the ETL is extraction, transformation, and load, right? So they're pulling out fields that they need, they're transforming them into the format that's in here, and then they're loading it into here, right? And it may not be that everything gets put into the database, all right? So if you need something and it's not there, they've got to go back and process all of this. The other point of this is if you're a data scientist out here, you're not getting anything from any of these sources until it's in this database, okay? ETL can take forever or too long. Let's just
A
say
quick
too long.
question about that.
Sure.
So is the approach now not to sort of merge to one row, like all these databases, so you have like one key ID, you just sort of feed an additional data set or additional database, an additional database, an additional database, as long as they're like a matching kind of code?
Yeah, so the approach now, specifically in the realm of big data, right, is to do something called schema on read. And what that is we don't make the data clean and in a uniform format because we say it's just not practical. It changes too often, right? You know, I've changed it, I've written the test for it, okay, great, oh, now it's changed again. What? You know what I mean? So, and now everybody has to wait again, right? So the approach, the newer approach, okay, is you basically have different landing zones, okay, right? So say, you know, for file 0 or format 0 goes there, and format N goes over there, and et cetera, okay? And then you have, you know, data scientists out here, okay? And what we are doing, all right, is basically going and getting this ourselves, all right? Now, the problem is the format over here is entirely different than the format over here, right? So we are figuring out what the schema is when we read it, right? And the idea is it's like picking your clothes. You don't know, like if we had some type of magical, you know, clothing that we could put on and just wear that for the entire year, that would be great, right? But you don't know what the weather's going to be. And you take hygiene out of it, right? Like you still have to make a choice every day because the weather changes. It's unpredictable. So we're constantly picking new clothes. Schema on write takes the approach of we've got to build a very, very smart piece of clothing for you to wear throughout this year, let's say. And schema on read takes the approach of it's very much like with neural networks. It's changing too fast. Put this on for now and then make a decision on it later. But you get to make the choice, right? And the other thing is you'll have to do the research to figure out what to read, what to where, okay? Just like you'll have to do the research over here to figure out, you know, how do I put these things together, all right? But what we have figured out is the time, all right? So time to get schema, all right, is significantly less than time to wait for the schema, right? Sorry, ETL developers and enterprise developers, it takes too long, right? It changes too fast, it takes too long. So, and on top of that, it's too big, right? So the other thing that's happened is these little folders, right, equate to something called data lakes. Anybody heard of these things? Right? Data lakes are nothing more. Oh, go ahead. Someone said something.
No, I mean the ETL is pretty tricky, and is there like out of box ETL pre-packaged that somebody can use? Because having somebody do ETL before delving into classification, it's going to be a headache.
Yeah, it's a headache. I mean, and here's the thing. I think that was Nana. So
it's Dana.
Sometimes it's necessary, but what we have found is that it doesn't scale when the data changes a lot, right? It doesn't work because, you've built this incredible system to try to get everything down to a single format, but it's changing underneath you. So what's the point?
Mm-hmm.
You see what I'm saying? And so now, if the system does not change that often, right? If the data coming in does not change its format that often, then, and you have, 4 or 5 sources, then you can use ETL. And listen, for a long time, ETL was the standard because it was better than us programmers writing our own routines to do it. And that happens, still to this day, right? But the idea is if the sources are, increasing, the variety of the data is changing, and there's so many new sources, you need a way to deal with that. And that's another issue that gets solved by horizontally scaling, right? Because you can say, you servers deal with this. And, we have the ability to automatically detect the types. And so this is another example of where big data and horizontally scaling comes into play, right? So we eliminate ETL and we start dropping these files, data, whatever it is, into these folders that are called data lakes. And data lakes are nothing more than, folders. Okay, so here's a folder, here's a folder, right? And the difference here is rather than you only having, let's say, 1 terabyte, okay, you are effectively infinite. This is what the cloud providers give you. Okay, Google, Amazon, Microsoft, whatever. They will let you throw whatever you want up there, all right? So you lose this highly structured database with all the fields that you want, right? But you gain infinite storage and you get access to the data, right? And this infinite storage is made possible by horizontally scaling, right? No way that you can store all of this on one box. This is the Hadoop stuff, right? And in short, it's HDFS, Hadoop File System. There are a couple of others, but that's the big one, right? So it allows us to take gigantic amounts of data and spread it out amongst these little, commodity servers, and it apparently looks infinite to you. So those of you who have been project managers or had to deal with systems will know that, there's a format change, and that may cause gigantic ripples throughout the system, right? That you'll have to wait, 3 months, 6 months, who knows, okay? So here you have redundancy. You may have multiple systems that have to deal with it, but they're not like depending on each other either, right? So it's a little bit rogue, right? But it is more effective because the data is changing faster. So what's the point? And we're seeing more and more data, so we need to be able to stick it somewhere that is basically infinite, right? So this is the variety issue, right? And the last one is veracity. So how are you going to ensure the accuracy of your big data? How are you going to make sure it's not crushed as the other 3 V's approach infinity? So volume goes, the velocity goes, the variety goes. How are you going to find a way to make sure that the data is still good? All right. Any ideas on how we do this one? This is the most interesting one to me. Anybody dealing with this? How do you guys, when you look at your data set, say this data is good or this data is bad? What do you do?
So like do some sampling checks or something, like sort of take a subset of it, verify that, and make assumptions that the other components are working in the same way.
Good way to do it. William, what happens if you have the world's data and you have to do that? What happens if the populations are different and it's harder to sample? What happens?
Could you just repeat it again? So you have a lot of data, you have big data, and you want to know if it's a representative of something. Could you repeat that, please?
Yeah, sure, William. So the question is, you have the entire world's data, right? And and lots of people want it. So you have all the volume, and you have the whole world trying to get it. Your Google, let's say, right? You have the whole world trying to get it, and the data is changing all the time. New web pages are coming up, all new formats. You've got to figure out how to get it in there, right? And make sense of it. How are you going to make sure or mitigate
changes,
bad or missing data within the data set? How do you do it?
That's a good question.
Yeah.
So yeah, that's a really good, because see the data is changing. So now bad data and missing data, how would you ensure that you mitigate this? Well, I really haven't thought of that, because normally you have data that is fixed, and the idea is that you take this fixed data and you clean it up in your ETA and then move on to the next level. Now, if the data is changing, that throws out a new task or a new challenge, which in the data that I work with, in fact, the data stock data it's normally very accurate. Well, I don't know. I mean, I really haven't encountered this. Normally, the ones that I've seen are data that is fixed, and then you either extrapolate, interpolate, or drop the missing data, or do something to the missing data.
Yeah.
And move it on. Yeah.
So William, let me give you another piece, right? Let's say you still have a final schema. The difference is, so William, you are one of these data scientists out here, okay? And this is the world's data. All right, so this is the world data, okay? And there's other people like you maybe who are trying to get at it, but here's William, okay? So here's William, right? So William's there, and you've got this, and so you've put the data together. You did it schema on read, so you figured out you've got a view of this data. There's some tabular view of this data that you have, right?
Okay.
And we have come to you. Your model is predicting something, right? William is predicting that COVID is going to be here forever. COVID is going to be forever. Okay. So William is predicting this, right? And we have come back and said, William, how do you know you don't have bad data within the system that is saying that? How can you make the claim? How did you check the data that you pulled into the system? How did you filter out what was bad?
Yeah, you got me on this. You really,
no. And so I mean, the jury is still out, but there are some attacks.
Yeah.
Right. There's some attacks to this. And
I would say check for whether there are nulls in the data.
That's one.
No, but the data, in fact, faulty data could be even numeric. It could be 999. I mean, it could be a value that to the naked eye might look right? So
that's right.
One way to do that would be to do this type of anomaly detection.
Fantastic. I mean, that's right.
Right.
That's right. That's one way to do it. Okay. And so, the idea is, are there any former Microsoft alumni in the room? So this is a famous interview question from Microsoft, right? So I want you to move this mountain. How are you going to do it? Anybody know? How do you move a mountain?
You don't.
A stone at a time. Yeah,
That's
Piece
one
by
exactly.
piece.
answer. There's
Piece by
another
piece.
answer.
Right.
Piece
Who
by
said that?
piece.
One rock at a time.
One rock at a time. That is correct, right?
Mhm.
And so now you need to figure out. So the answer is right, and that was the answer to get into Microsoft, right? But the answer is incomplete because you have to figure out. I mean, that's there, but now you need to figure out which rock to move, right? You got to prioritize this. You have the world's data. So which rock are you going to move? And that comes from anomaly detection. Let's deal with the stuff that's truly weird first, right? Let's try to get at that. And anomaly detection can be done statistically, but it is superior in all regards through machine learning. Now, how are you going to do anomaly detection with machine learning on the world's data? Do you think you can vertically scale that? That's right, too big, right? It'll take you forever. And so there's another example where we use big data to fix big data, right? We've got to vertically scale the models out to look for anomalies within the gigantic data set that William is looking at. See? So that happens. The other thing that happens is, make no mistake, the search engine providers and large models in all organizations have human beings looking at the data, right? Google has hundreds of people looking at that index to make sure that nothing crazy gets in there. This happened with Microsoft, right? A whole bunch of stuff that was, totally derogatory got into the index and their chatbots, and it went rogue. Started saying all kinds of wild stuff, right? And they quickly had to pull that back, right? So, you need humans still, for now. We still need them, all right? So the combination of anomaly detection and people looking at records. Now, when you have people looking at these records, right? So let's say we have, this person, and this person looks at the records in here and says, this is bad. Okay, so, and then they say, maybe they come up with a list of, I had this record and, these records, and this was bad, and this was good, and this is bad. Is there anything we can do with this list? What do you guys think? William has gone through. We locked him up, right? And we said, William, you are going to have to figure out all the records that are bad in the world's data. Okay, so he didn't see the sun for 2020. He read everything. Okay, and he said, all right, I have found these records, and I think that these records are bad. Let me not just say good, because there's a whole bunch that's good. So he found them, and he said, here are the records that are bad. And you know what? He needs some good. So he said, here are records that are good, and here are records that are bad. He broke them both up. We need both. So William has gone ahead and categorized these records, right? And William, being the only person that we could possibly make do this, and would do it, we take it as gospel for now, right? Is there anything we can do with this list that William has created?
I think
What do
you
y'all
can try
think?
to identify the commonalities among the bad lists,
And how would we do that?
breaking it apart again and trying to see, sort of like the neural network, doing the same thing with that.
Yeah, that's right. That's right. So if William if anybody in your organization is building lists of what's good and what's bad, or what's X and what's Y, right? That is training data. If it's in Excel, right? If it's beyond some threshold, that is training data, right? And you should immediately try to get those people that are doing that to work together, and then take that data, vet it if you can, right? You may have to use a consortium of some sort, vet it best you can, and then run that through a classification model, right? If you have people labeling data, good, bad, red, brown, whatever, right? Get that data, preserve it, identify it as training data, and run it through a classification model, right? So, it turns out William may have figured out what world peace was, because we figured out what was good and bad, and then we eliminated bad advertising, and now everybody's doing good stuff, right? So, okay, so the 4 V's of big data, right?
I have a question.
Yes.
Would that be similar to the gradient descent? Because from the previous course that we had taken, I know she mentioned gradient descent in terms of trying to get to the lowest degree or minimize. Would that be similar, a back propagation?
Yes. So vector gradient descent is a tool that you would use as if you were using either regression or you were using neural networks for back propagation. And it's important because that tells you the weight that the individual neurons need to be in order to meet the accuracy demanded by the test data. So let me try to distill that, right? So let's say that we have some neural network over here. It takes 2 inputs, and let's say it has, 2 hidden layers, and it has 2 output layers. Okay, so let me just connect things here. All right, 1, 2, 3, 1, 2, 3, 1, 2, 3. It's going to look wild, but you guys get the idea here. Okay, here, 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 here. Okay, sort of a mess, but okay. So you feed in some input. Okay, let's say that this is William's version of the world. Okay, we feed it in here. We don't know what's going to happen. Okay, but we feed it in. All right. Now, for neural networks to go, actually, here's what's happening. Okay, you're going to feed in all data that's in the world. This is a little bit different in the deep learning case. And out here, the key to all of this is the test data. Okay, so what happens in the test data is William has gone ahead and said that when you see advertising and it has to do with cigarettes, okay, whether it is a real ad with cigarettes or not, it equals bad. William did this because he's a genius, okay? And so he's gone ahead and said that, right? So what happens now is we're going to send through all the world's data. There it goes. And one of those records, more than one, unfortunately, is going to be, when you see an ad and it involves cigarettes, right? And what will happen is we will ask this to make the prediction of whether it is good or bad, okay? And there's going to be some training data out here for this as well, right? All right, so that'll have some examples of, it's advertising and it's, let's say, cigarettes is bad, advertising is, I don't know, let's say alcohol is bad, whatever, right? There'll be various examples out here. But this data is not really curated. Williams basically looked at the world's data and written like good and bad, right? He's not done any like engineering to that data. It's just, here's a whole bunch of ones and zeros, literally, right? And that's the big difference between neural networks and traditional machine learning. Traditional machine learning, I only have 5 minutes to teach algebra. I have got to make it nearly perfect, okay? In deep learning, we say it's too much, and I'm not even going to try to make it perfect at first. I can't possibly teach, well, in general, it would be hard for me to teach, let's say, an 8-year-old all of algebra in 5 minutes. Some of you have this capability. The rest of us have to suffer, okay? So what happens is we give it to you over and over and over again, and that's what happens here. William cannot feature engineer the whole world's data, too much, but he can label it, right? He can say, this is good, this is bad, etc. Right? And then what will happen is it goes through the neural network, right? And it's going to make a prediction, right? And so each of these things have weights. This is where the gradient descent comes in, okay? You have weights, I plus 1, etc. Right? X, Y, whatever. And those weights govern whether or not that node is going to fire. Is a signal going to go through here or not? Okay, how important is this factor? All right. Okay. So it'll come out with a prediction, and if it says that ads that have or cigarettes are in fact good, then we will send this thing back, just like you tell a child you're teaching, no, that's incorrect. And then they'll say like, well, why is that wrong? And they start to reason, and the neurons in their brains change, right? And that's what happens over here. It starts to reason, right? And reason in terms of what do I need to do? Here's the reasoning. What do I need to do to these neuron weights, okay, in order for all the values that William labeled as good or bad to be verifiable as good or bad in the test data? And the test data is going to have some data that was not in the training data, right? So we don't send through, this is before the model goes completely live and we're running everything through it. We send through a subset of the data, okay? We don't have all the ads on cigarettes. We have some of them. And so what happens is the network will be trained, and then you'll send through, well, you're training it, and you're going to send through this data, and you're going to have a data point that's not in the training set, that's in the test set, that has this, it's an ad and it's cigarettes and it's bad. And if the network does not predict that, then it goes back and starts to adjust these nodes, right? And it could do it two ways. Two ways to do this. First way, brute force, right? We're going to take every possible weight between 0 and 1, and we'll use a precision of 2 decimal points, and we'll consider all possibilities, right? And that works so long as you have like a supercomputer, if you have a lot of nodes, because you're basically doing the Cartesian products, right? You're looking at every single combination there is in order to pull off the optimal result, right? A better way of doing that is using vector gradient descent. And what vector gradient descent is, it's that it senses, like you'll have some accuracy, okay? And you want, let's say this is error, right? And then let's say this is the weight, okay, for that particular node. Vector gradient descent basically allows you to arrive at this point by using calculus, right? And here's how it happens. Okay, did you guys get into like the mechanics of vector gradient descent in the prior lecture? Sort of. So there's a trick, right? And it's an assumption, and this is one of the maybe the drawbacks, but it's an assumption of functions. It goes like this: if you guess, you have to guess. That's what we do in computer science. Like we don't know, so we guess. And when we say that things are unknown, we say they're random. All right. But the attack is you pick a point, some weight, right? And so you've done the trials. Okay. Your job is to find this low point now. Okay. And this is a simple example because it's just one of the weights. You have to do this for all the weights, right? But the idea is you pick a point on the curve. Okay. If the point you pick, if the point to the left is less than you, right, that means that there's more way to go to the left. And if the point you pick to the right of you is less than you, that means you're somewhere up here. So you need to go down this way, right? And so this is achieved by trying, like, basically finding the derivative at certain points, right? And that's why it's called gradient descent, because there's more to it, right? But you're basically finding the slopes at these points, right? And that slope will tell you, not so much the points, right? But the slope will tell you, okay, I'm positive, the line is going upward here, the curve is going upward here, so let me go backward. And if I'm over here and the slope is negative, that means, oh, okay, I am approaching the point correctly, right? So you calculate the gradient at each point, and that helps you figure out how to get there faster to the optimal point, as opposed to doing every possible combination, right? So that's how we use it. Now, vector gradient descent is what makes neural networks go, for now, right? I don't know if we talked about it before, but quantum is like already here. Okay, Google declared quantum supremacy. All right, and that is a big deal because they're solving problems that would take 30 years in 3 seconds. Right? They 2 to the 70 qubits. 70 qubits, right? The storage unit of a quantum computer, 70 units of that is enough to store the entire world's data. Right? And what that means is they're going to be able to do a whole lot of calculations in parallel that we could not do before. Because, you know, keeping track of things in parallel means you have to keep track of it. Right? So if you have a billion, let's go back. So let's say that Kenneth is built this system, and at first, you know, having 10 servers in horizontal work for you. Okay? But now the aliens have decided that your data is of high value. Okay? And the galaxy wants your data. Okay? So what are you going, and you've done the math and you say, okay, in order for me to provide this data to the galaxy, I need 1 billion servers. More servers than possibly are available. Okay? So, but even if we got it for you, Kenneth, right? How are those servers going to keep track of where the jobs are now? Because that itself has become a big data problem, right? I need to know what this million servers are doing so I can schedule back. All of that's got to be stored in memory, right? So what this quantum computing stuff does, it's not so much that it's faster, it's that it allows things to happen in parallel at a scale we've never seen before. That's the trick. It solves the memory problem altogether. Done. We can store everything, okay? That also means that we can run in parallel like maniacs, right? So once that happens, all right, brute force computation will take over. And you know, vector gradient descent won't be as important, right? We'll just crunch it. Big deal. We can get at that in 2-3 seconds, right? As opposed to 30 years, right? But now we don't have that, right? We don't have it yet. It's still expensive, but they're here. NASA's got one. Google's got a couple, right? You can, you know, AWS has a couple of these things. So it is arriving, right? It is arriving. Okay, that's a lot on vector gradient descent. Effectively, it makes things go in neural networks by using an optimization step that allows you to set the network's weights without having to consider all possibilities. I hope does that answer your question? I apologize for being long-winded. Yeah.
Yes, it does. Thank you.
Good. Yeah, you're welcome. You're welcome. Yeah. So, but a great question, right? This is what makes it go currently. Okay. So where are we on time? Do we end at 1:30? What is the scheduling for today?
It's 1:30.
1:30. Okay. So does anybody want to take a 5-minute break? Or do you guys want to power through? Raise your hand if you'd like to take a 5-minute break. All right, let's take a 5-minute break. All right. We'll come back at 12:30 and then we'll step into some code. I'll walk you through what this stuff looks like in practice, and we'll see a classification model that works on big data. Okay, cool. See you in 5 minutes. Yeah.
All right, John.
Okay, so I'm good here.
Yeah, hello. Whilst we wait to continue, if you created a Terra account that is needed for Module 8 next week, please just type yes in the chat area so that I have an idea of the number. Thank you.
Okay. All right. So let me walk you through an example. I'll post all this so that you guys can go through it as well. For now, I'll take you through. And let's start with DAST. Right? Conventionally, we start with Spark, but you know, DAST is interesting, right? So most of you have seen pandas, right? As we've gone through the course, there's some pandas in Python. So you'll be, it should be pretty familiar. And DAST does some things that other frameworks don't do, which I'll also show you. Okay, so, all right. Okay, so the notebook I'm going to walk you through, okay, is a decision tree notebook that tries to predict what Tesla stock is going to do. And by predict, I mean, or by do, I mean it's either going to go up or go down. Okay, and the notebook shows you how we go about feature engineering, right? So you've seen some classification models, right? You've seen decision trees, you've seen neural networks, right? I'll walk you through how these things are actually built, right? And I'll also show you how it works when you're in a situation which requires big data, okay? Okay, so the first thing is the installation for DAST is much simpler than the installation for Spark. Indeed, the situation for the installation for Spark is quite daunting. You're going to need to have Java. You're going to need to set environment variables. You're going to need to have to install Hadoop. And you know, when I teach the subject, it takes students somewhere between 20 minutes to a week to get it going, because it depends on your environment as well. Like it's actually not very friendly for Mac. Mac students have the hardest time with Spark. Dask is quite literally pip install dash complete or conda install dask, and you're there, right? So if you have a Python environment going, like the majority of the work is done. Okay, so all right, so here are the Dask imports, right? Really, you're gonna see data frame, and you're gonna see client in this notebook. These are here for some debugging we did earlier. Pandas and NumPy, everybody's seeing this, data frames, classic data frames, and NumPy for math libraries and their arrays. NumPy arrays are everywhere, okay? And then I like to be able to see all the columns in my Pandas data frames. So I always set max columns to none as preferences, okay? Okay. And then over here, what we have is, let me comment this out. All right, so then over here, we have some glue code to sort of release an existing Dask connection and create a new one. Or if there isn't an existing one, create a new one altogether, okay? So, and once you do this, okay, so we have this UI that comes up, and let's go there. Okay, so this is looking at So there's quite a lot going on here, right? So what Dask does for you is it puts out this UI, and it shows you what tasks have been done by which core, right? So each of these divisions, 1, 2, 3, 4, represent a core on your machine. And so that comes back to over here. So you have 2 workers, okay, and threads per worker are 2, and then we've set a memory limit, right? But if you come back to in system here, workers, yeah. So what's happening is and so this is an example that's on my laptop, right? But were you using it in practice and you were using it on a gigantic data set, instead of this address being, you know, my local host here, it would be the servers that are running Dask for you, okay? And again, what we do is we take a large piece of data and we spread it out amongst these other servers, and then we have this coordination going on back and forth where we're able to run operations on each of those data sets and then bring back results. And that is important because that is how traditional machine learning works. We spend a lot of time massaging the data, building up these features, the independent variables, so that we can get a really good result in the dependent variable, right? And that's because traditional machine learning approaches are, I only have 5 minutes to teach you algebra. Right? Let me get it as perfect as I can, okay? All right, so 2 CPUs, each with 2 threads, right? And so there's 4 threads in total. And that's why over here you see 1, 2, 3, 4, okay? And this is from a prior run, right? So you'll see when things actually start kicking off over here, how things are running, okay? All right, so, and then I'm going to try to keep this in sight for you so you can sort of see how things are running here. Let's see this. And yeah, you really need to see this one, which we can see from tasks, I think, straight away. Yeah, okay. So there's tasks. So I'll keep this over here for us. All right. And then I need to make this a little bit smaller as well. Oh, I don't want to do that. Hold on. Let's do almost there. Okay. All right. So that's pretty close. Oh, okay, never mind. I just moved that over here. Okay. Let's run with this for now. Okay. So we have this cluster up to help us process, okay? And, you know, it's sort of business as usual, right? So we're going to read in some data. Now this Tesla long data, this is just the stock prices for Tesla for, I believe it's 2019 and 2020. So it's open, high, low, close for each day, right? So we read that in. Oh, it's actually changing over here. Okay, and it changed there. All right, so you'll see these tasks. I'll come back and sort of explain what's happening over here. But let me walk you through the notebook, and you'll see Dask executing tasks in parallel, which is really what this is all about, right? Can we manage this, you know, large, big data problem by parallelizing and spreading the data out as well? Okay, so we read it in, and we got the first row, right? Data.head. And so it's the date, the open, the high, the low, the close, the adjusted close, and then volume for that day. Okay, great. And what I'm going to do is convert the dates to date times, and that is because Dask reads in dates as objects, right? And that becomes tricky when you need to do some date manipulation in this notebook. So if you convert to standard date time, that makes it much easier to use existing pandas and NumPy libraries to perform the date manipulation, right? So, okay, so we convert the date column, right, which is this column over here, right? So this is basically, Panda syntax. We're going to say the frame, the column that we want to update, and we're going to set that to be date time, right? And we're doing that on the date column for this frame, okay? So convert this date column to date time and assign it right back into date so we don't have an extra column, right? So we do that, okay? And if you notice, nothing moved out here, okay? And I'll explain why that is. DAS does this thing called lazy evaluation. And if you also notice over here, when you output, when you leave the data frame as the last entry in a cell, you should automatically get the data frame's head, right? So you should see 5 rows. But we didn't see that here, right? And the reason for that is Dask has something called lazy evaluation, okay? And that is very important because let's say you render this thing, okay? And you have it, and it's now in memory. Okay, you run through it and you calculate this, and so you get the head, and to get the head, that means you got the data set, and so, or at least the first couple of records. But let's say that you process it, okay? Then what happens, and head is a simple example, but let's say we wanted to take average here. Same thing. If I had calculated the average of this data frame, and it's gigantic, it's now in memory. So let's say it's 13 gig. And I only have 16 gig available, okay? So if I calculate this at this moment, and let's say I also read in another data frame and I calculate that at this moment, I may have 13 and 13, and I will have gone over the amount of memory I have access to, okay? So what DAS does is it doesn't calculate these things until you absolutely need them, right? So it calculates it at one shot, and it manages the memory in and out in a way that if it's not enough, it'll page to disk as it needs it, right? So, and there's a series of optimization steps that happen here, but that's the basic idea. You don't want to allocate the memory up front. You want to have the Dask engine find the most efficient way to manage these large amounts of data for you. It's very simple, very similar to how explain paths work in SQL queries, right? You don't want to be managing where they're going to build the indexes and, how they're going to shuffle the data, right? You basically write the query, and the query engine then finds the fastest path, most efficient way to get it back to you, right? Same thing happens here within Python code with Dask. Okay, so, and you running the query is basically you running an operation here, right? So because I've not called head, I've just listed it. It doesn't tell me what the values are, but it does know the data types, right? And that happened because it surmised it from back here where it read in the data, okay? And we took head on it. And it also knows that I've made this operation where the column is going to be a date time, right? And even though now it's object, but it will do this when the entire evaluation takes place. Okay, so, all right, so we've done that, right? So we don't see the data, but we see the types, right? Now, to figure out why Tesla does what it does, and this is just an example to sort of get you familiar with it, how these classification models work, is we can look at Tesla's fundamental data. People will say it's not the technical analysis, it's the fundamentals, right? And, definitely to build an accurate model of how this stock is going to move, you would need many, many, many sources. Macro sources, micro sources, supplier sources, all kinds of stuff would have to go into it. But this gives you a feel of one of those sources, and that source is Tesla's fundamentals. And the fundamentals are, what was its revenue? What were the gross margins? What were the assets they had? right? Things that basically go on the SEC filings for earnings. Okay, so we're going to read that in, okay? And the idea is, can we look at Tesla's fundamentals that it's reported for the quarter, right? So the report has come out, this is what the fundamentals are for the quarter. And based on the fundamentals, can we predict if the stock is going to go up or down, right? And that's interesting because let's say that it's about revenue, right? If the stock is going to have good, revenue growth, then then the stock is going to go up, right? But it may be much more than revenue growth. It might be revenue growth and margins have to not drop because you can increase revenue by lowering your margin, right? So the hope is that it will give us the factors you need to predict what makes the stock go up or down. And then the thought on that is, if it's something that, if those factors are predictable, then you may be able to get ahead of it. Let's say it's revenue, okay? Well, Tesla publishes the amount of cars it sells almost 15 days ahead of its earnings report, right? So if it sells a bunch of cars, much more than it sold than the last quarter or, from the year before, then you can say that revenue most likely went up, right? Because that's the incoming, right, sales. So if you see that, and that was a very good mark, then maybe that has, and if that's the factor that we come up with, then we can say that car sales, which impact revenue, impact the stock going up or down. And you can make, predictions about what happens, right? At least at a quarterly level, right? So that's the idea of this, right? We're going to try to put the fundamentals together with the stock price and see if we can see which fundamental factors, if any, have a bearing on what happens with Tesla. Okay, so, all right, so let's read this in. Okay, and again, you can see nothing happened, but if we had taken head here, all right, I think, yeah, see, now operations are happening, okay? And, this thread did this, it read the CSV, right? And this thread over here rendered the head for us. So you can see that there's this split of who's doing what, right? Already in the background. Okay. So, all right. So, and then you can hear the data for us, right? Looks just like a standard Pandas data frame. And DAST under the hood is a job scheduler, a graph engine, and a data frame abstraction that is basically a whole bunch of small Pandas data frames. And that's the genius of DAST. They didn't create a whole new data frame API. They extended the Pandas API, and half the developers on DAST are Pandas developers because they know that this big data issue is gigantic, right? And if the library is going to go ahead and do it, then it might as well be Pandas because Pandas and DAST work together, right? Very friendly environment with these two libraries. Okay, so we have that, right? So we convert the time here, but you actually don't need to do this. So we have this because, well, no, we need to do this. We need to do this because it reads it in. It reads it in as an object, right? So now let's go ahead and convert this quarter end date, right? So the file before had date, right? So it's just this date column here, right? The fundamental data only has quarter end because the fundamentals are reported quarterly. Okay, so we're going to convert this also to be date time so that we can do operations on it, right? So we've done that. Okay, great. All right. So now we have date time 64. All right. Again, I didn't call ahead on it, so you're just seeing this operation. You're not seeing the operation execute, and you're only seeing the data type. Okay, we've got that. All right, great. So now we're going to join the two data sets together, the two DAST data frames. Remember, DAST data frames are nothing more than a whole bunch of Pandas data frames. So to do that, you can call merge. Okay, so we're going to take the stock data, and we're going to merge it with the fundamental data, okay? And the stock data, we're going to use the key of date, and the fundamental data, we're going to use the key of quarter end, right? And again, we're not executing it because we haven't called head, or we can call compute as well. But we're just going to do this, and nothing happens out here, okay? But to illustrate the point, if we now call joined.head, right, you'll see, I'm actually going to close it on this other window because it should move there. Yeah, there it goes, right? So let me close it here because I think I have it on 2 windows, so I think it'll happen faster now if it's here. Okay, so now you'll see that there's executions happening, and this one actually went to a whole nother core, right? So we read the CSV, little 2, so let me see if I can zoom in here. I get a read out of it. We assigned, right? We assigned it to join. And now let's jump back out. Here. Quite a bit in here. Okay. Okay, and then over here, that was the head operation. Okay. So, okay. So we have that. So you can see things are happening in parallel, and then another step occurs. Okay. So now we have the join of the stock data, open, high, low, close, along with a bunch of fundamental data. So I'm going to actually let this go in the background and make the screen larger for you, because I think you guys get the gist that stuff is happening. And then we'll come back and look at the DAS scheduler and how it executed this whole thing for performance towards the end of this. So let me, I got to pull this window down. I just want to maximize this. Is that it? No. Hold on. All right, I'm going to pull this out. And then I'm going to do this. Okay. All right. So now we have it. And so there's a whole bunch of data in here, right? Goodwill and intangibles, long-term debt, earnings available for common stockholders, et cetera, the EPS, a whole bunch of stuff, right? Okay. And, okay. So the idea is you want to figure out what happened after earnings, right? Earnings came out, the fundamentals were displayed. What happened to stock on the next day, to the stock on the next day? So simple model, but an idea, right? Did it go up or down after earnings? So to do that, it's just like pandas, right? We can create a column, and this is feature engineering now, right? So we're going to create a column called next day, okay? And it's going to take the current date, right? So this is the 31st. This is actually 2015 and 2016 data, yeah. So it's going to take March 31st of 2015, and it's going to add 1 day to that, right? And let's do this. I'll put the and back in. And that gives us the next day, right? So we have the join of fundamentals and stock data, and now we're going to compute the next day. Okay, so we compute the next day. So it's cooking. Okay, great. And we called it next day, right? So you have this, 2015 331. Now you have 2015 401. Okay, April Fool's Day, etc. All right, so we know what the next day is, but now we need to go get the data for the next day, right? We need to know if it went up or down, right? So now we go and get the next day's, get the trade info for the next day, right? So how do we do that? Okay, so we have this data frame called joined, which has fundamental data, stock data, and the date of the next day, right? So now what we need to do is join this big data frame we have back with the original stock data, right? The original stock data had every day, right, in 2015, 2016. Go back and join it on that, right? And join it on next day, which is the field that we've computed, so April 1st, okay? And join that on date, okay? So what's going to happen is when you do this, it's going to get you all the stock data for 2015 401, and the day after all of these days. Okay, so if you do that, let's get ahead here as well. Okay, right. So this is for the first one. Okay, and before we had, and you can see DASC has done us a favor, right? So we had these columns, date, open, high, low, close. When you join with a data set with similar column names, there will be conflict. So DASC is, and Pandas does this as well. DASC is labeling the left side, the original data frame, so join for us as X _ X, so X and Y, right? And the new data that it's brought in, okay? So we have next day, and now you have date Y, open Y. This is the stock data for the 1st of April, right? And it's labeled a date _ Y, okay? So now you have fundamental data, the price on the day of the fundamental data, the next day, and the next day's stock price, right? So now you have, what happened after the fact, okay? And, okay, great, so we have that, right? So how are we going to figure out if this thing went up? A couple of ways to do it. Simplest way is to take the percent difference, right? And you could always put in like, I want to say it went up more than 5% or whatever it is, right? So for this example, I just set it as the percent difference. And what's wonderful about this is if it works in Pandas, it almost, and this is the catch, it almost always works in DASC, okay? There are some things that Pandas does that DASC does not do. We'll see an example of that in a second, okay? So, but simple things like this where you're calculating, so if this is just the new price, the next day's price, minus the prior day's price divided by the prior day's price, right? And it's just, I don't know, it's just wonderful that we can reference these things like this. So we know the data frame is called next trade. You can just say dot whatever that variable's name is, and this will calculate it and set the difference, right, in all of the columns that you have, right? So we have, I think, 5 columns. If I do this again, though, it will join, so let me not do that. So we'll do it here, right? So next trade, and we'll show it. So you can assign this way, and okay, so it cooks, and now you have original stock data, fundamental data, data for the next day, and you have the percent difference, right? So you're building up, the 5-minute algebra course for that child, right? You're trying to make this model as smart as you can with an initial set of independent variables. Data science lingo, we say features, okay? But the reality is these are independent variables that we are curating for the model, okay? Okay, so now we have the percent difference. And you can see that on this day, right, and, the free cash flow per share was some value, and let's see, there's something we can find. So book value of equity per share was a certain value. So, can we discern a pattern within these independent variables that predicts whether or not it went up or down? Right, so like here it went down, next day it went up slightly, here it went down, slightly up, okay? So actually this is 3%, this isn't percentage, so 3% is considerable, right? Down 0.3%, down 3%, up 3%, up almost 2%. In a day is considerable, right? So, okay, so you have this difference, right? Now here's the part where it comes to classification. You want to be able to say, is it going up or down, right? So one way to do that is create another field, and that's what we're doing, right? We're just adding to this data frame. right? And you could drop some of these values as well. You'll see that we don't use all of the factors, and that'll make it more efficient. But we're basically adding these fields in as we go and making those fields more and more meaningful, okay? So we're going to create another field called went up, right? And if we'll set it initially to 0, and 0 means false, okay? And here's the part that does not work in straight pandas. This is like the gotcha, okay? So in order to set went up, it's a conditional value, right? So the idea is you want to look at the difference column, the next trade difference, right? And if it's greater than 0, set it to 1. Means it went up. And we could have set it to whatever. I like 0s and 1s because they save more space. You don't have to do one-hot encoding later. So I tend to deal with 0 and 1 for true or false values. Right? You could have set this to false, and you could set this to down, and you could have set this to up, whatever you want. Okay. Okay. So we set it to, if it's greater than 0, be 1. If otherwise, by default, it's 0. And you do this to the went up column, right? So this is you setting it, right? And in DAST, you do this thing called mask, right? So you're basically taking this value and you're putting it into went up, and then you assign that into the column. Right? It's a little bit long. This is like the most tricky part, but the same thing, the exact same syntax, the syntax is similar in pandas. Were you to do it in pandas, you'd have done something like this. You'd use loc, right? So find it, right? And then assign it into the column. In DAST, you have to do this mask issue and then assign into the column. This is the only difference that exists popularly for data frames. Most of it is very close. So conditional assignments, you have to use mask, okay? The good news is that mask exists in pandas as well. It's just that loc is a little bit more natural and efficient, right? Okay, so once we do this, we should get a 1 or 0 value for whether or not the stock went up or down, right? So if we do that, okay, yes, and so let's just look at this data frame now. So again, no evaluation, but now there'll be an evaluation. Okay, so the date, the stock price originally, the fundamentals, the next day's stock price, the difference, and now whether it went up or down. Okay, so you've got some label data now. Okay, once you have label data, fantastic. It's time to send it into a classification model. And I always like looking at decision trees because without the amount of options in the labels exploding and the permutations in the data set, they're understandable. Some of you, has anybody built a decision tree, like professionally here? Okay, yeah. So, William, do they fall down ever for you? When do you have issues with the decision trees? Or, yeah.
So when do you have issues with the decision tree? Is it when the tree becomes too big, in which case you have to prune it?
Yeah. So what happens is there's two things. One, which is very sneaky, okay? And there's a midpoint calculation that occurs, which is largely one of the big reasons why we go to other models, okay? But the issue is when you have so many nodes in the tree, it will start to look like the screen of the matrix, like bits and bytes flying by. It'll become, unintelligible. And that doesn't help with the explainability of the situation, okay? So it's explainable, but if you were a computer, only would you be able to manage it, right? And we're talking about, there are decision trees that are, and there's one that I'm working on now, which is like 3,000 nodes. Like you would have to, do a dissertation to get through parts of it. It's unbelievable. And so then the question is, do you even want to use a decision tree, right? And random forests come into play, but they have the same issue. Like they really help with overfitting. So then you have to question why you do it. Now, that we'll get to that, but for right now, if your data set doesn't have that many options and the tree is manageable, then you can use this to get some insight, right? And our data set is not that large and unwieldy here, so you can get some idea as to what it is visually. Also, even if you can't see the tree, let's say it's gigantic, okay? You can still print out in a data frame the tree's most important factors, right? So you'll see the tree, and what happens is the split that is closest to the top is the most predictive of the categories, right, of the independent variables. And so even if you can't see the entire thing, you'll still be able to get a printout of the most important variables and use that as a good marker, right? Like now we know that it is in fact total assets or something, okay? So, okay. And we'll get into the sneaky midpoint thing as we go. All right, so we have these labels, all right? So now normally, and you can see this is, from a Spark setup, you would have to go from a Spark data frame to a Pandas data frame. Okay? Now, when you do that, first, you may not be able to do that, right? And that is because the data frame is so gigantic that once you go to a Pandas data frame, it'll blow the box, right? There's not enough space on the machine. You'll run out, okay? Okay. The other thing is you have to basically use all of Spark's libraries. And so it's a different way of doing this kind of work, right? So here, right, you don't have to convert from a DAS data frame to a Pandas data frame, right? It happens for you automatically because DAS data frames implement the Pandas data frame interface. But don't be deceived by it. If the DAS data frame is colossal, okay, you will not be able to run this part, right, of converting into a, actually we're not there yet. When you get to the machine learning section of this book, you may have performance issues if it's colossal. Now, there is a way to do that by setting DAS to be the process for the sklearn algorithm you're using, right, or the Python algorithm you're using, and we'll get into that. So, but the point here is you didn't have to convert, right, but know that there are issues with converting, okay? Okay, so we're getting the labels, all right, so let's get these labels, and so that you can see that, and we're still in a DAS data frame now, right, so let's put out the labels, and labels are just going to be the DAS series structure, and we haven't evaluated it, right? Because it's, you have to call it like head or compute or whatever it is, right? So, okay. So, and then we're going to get the features, all right? And now the features are the independent variables, right? So you can't take everything because if you took diff, obviously when diff is positive, it's going to go up, or if it's negative, it went down, right? So you have to be exclude out the variables that are effectively equivalent to the dependent variable, right? So, this is just me taking a couple of them, but you could have chosen everything in there and you'd have been okay in the fundamental data. You just didn't want to take diff or the calculated columns because that will obviously give you this equals that, right? They're the same thing. Okay, so we do that. Okay, so now you have the features, okay? All right, so we're going to get just a data frame of the features. You need that because you're going to send these in as the independent variable, right? So this is X, and the dependent variable will be Y. All right, so we get that, all right? And let's go ahead and feed head here so you can see that. Okay, so here are just the independent variables, right? This is what we're going to send through. And we want to know if there's some type of pattern that exists in here that predicts whether or not the stock went up or down, right? And we know that this combination is associated with, I think it was up, and this one down, etc. Right? We have them, right? Those mappings are there. Okay. So, and the decision tree will find it for us, right? Okay. And some bookkeeping for figure size, more bookkeeping for figure size, just setting it up to be large enough. Okay, and here are the labels for Y. So down, up, up, right? So these map to this. And what's going to happen is the decision tree is going to go through each of these combinations and say, okay, which one of these factors best predicts this, right? Is it that every time current assets is something, it's up or down? Is it every time that liabilities is something? And it's probably not every time, but there'll be one of these that is a better predictor than others. It'll choose that, and then it'll continue to narrow down the next variable and the next variable until we end up with the actual nodes, right? So here are the values. There's nothing left for us to go through. This is as close as we can get. And these things do, in fact, predict the labels, right? So it ends up at a point of consistency that predicts the labels. More on that in a second, right? And we can get into the internals if you'd like to, no problem. So, but I'll get you through the notebook and then we can sort of open it, right? Okay. So, all right, so then X one more time. All right, now we're going to fit it, all right? So there's a decision tree classifier here. We're going to fit it on X and Y, all right? All right, so we have that now, okay? Now, when you call fit here, all right, X and Y are DAST data frames, okay? And it's, you know, these things are distributed, but, you know, unless they've been special, and you can see that from the DAST graph, when we did this fit, it wasn't a DAST operation. This was a fit in pandas, and not pandas, but in sklearn, right? So this you have to be careful with, right? So you've built this massive data set, right? And you put together these features, which you would not have been able to do, let's say, in standard pandas, okay? And let me make the point this way. We frequently use Spark and Dask to build up the features we need, drop the rest of them, okay? That reduces the size of the data, and then we send that into the model, all right? So you may have had 30,000 columns, and we may have used those 30,000 columns to make some calculations. And we maybe only needed 15 of those columns and maybe a label that we created, right? Just like we used went up, and we only used went up. We've kept went up as the label, and we've created some columns along the way to get at that, right? So you can then filter that data. Like, we've not taken all of this, okay? There's some things that we've had some ideas about here, and there's ways to figure out what variables to try to filter on, right? And that down selects you, lowers the size of the data, and then you can come to sklearn if you want to, right? Now, there's also ways to do this in Spark purely and in Dask purely, but the problem is the libraries are nowhere as rich as sklearn or Keras for deep learning, right? They only have a small subset of these things because it turns out vector gradient descent in parallel is actually quite difficult to do, right? So, but if you can down select and get it into memory, that works. And that is a frequent approach that's taken, right? Okay, and that is what we're doing here, okay? So we have this model now, right? And then it's basically par for the course, right? So we're gonna get the labels that we need, 0 and 1, display max columns again, one more time for the features, and then here comes the decision tree. Okay.
Hey, Prem, I
And
have
so
a question.
Sure.
So when you do the decision trees, so are you saying we don't have to do manually select the features ourselves? The decision tree just figures out the best features to use based on our data set?
It can, but there has to be some selection to make sure that you don't choose a variable that is effectively the dependent variable, right?
Right.
So you have to remove that, okay? And then
Okay.
over here, yeah, so you remove the variables that are effectively the same. Then you can send through every other variable you want, right?
Okay.
I did this to just make this more, legible, right?
Right.
But
Right.
you could have sent through the entire fundamental data, no problem,
I
right?
see. I see.
And then what happens is, and we'll get into the internals of this so you guys can see it. Then what happens is it goes through and identifies of these variables that you've left here, these are the ones which are the most predictive. Technically, we say have the least entropy or have the most information gain. But what that really boils down to is if you had to pick one variable that's predictive, it doesn't work all the time, but non-controlling interest is the most predictive of these variables. And current assets is the next most, right? So does that answer your question?
Yeah. What about normalization? Do we need to normalize the data, or we just kind of like just put it there?
You can just put it there, right? And so with neural networks, you really don't have to do much of that at all, right?
Right.
But here, it's you don't need to normalize this because they're different. They're also going to be different fields, right? So one might be dollars and one might be, units of something, right? Like margins is a percentage, right? So yeah, so there's some feature engineering that goes on here, but with variable selection, you just have to eliminate the variables that are obvious. Now, that are effectively equivalent. Now, when you run a decision tree and you start seeing something that always predicts correctly at the top, you may be in a situation where that variable is effectively the same thing as the dependent variable.
Right.
So, for example, with basketball, if you were trying to predict wins and losses, and plus or minus was in the independent variables, plus or minus is a perfect predictor because it tells you how much the team won by, right? So if plus or minus is positive, it's always a win, right? And if it's negative, then it's always a loss, right? So in that situation, you've got to carve it out. But for the rest of them, the decision tree figures it out. Actually quite ingenious, but it comes at a cost, right? It comes at a cost. So here, I'll walk you through the decision tree, and I'll talk about the cost, and then we'll open it up. But does that answer your question?
Yes, thank you.
You're welcome. Okay, so what this has said, and this is a small sample size, right? We had 5 quarters of data, but it's basically saying if the non-controlling interest is less than this number, right? So this is, these numbers are, nobody should have this kind of money. All right, here we go. So 44 million, right? And this could be in shares, right? So I think this is, if non-controlling interest is less than 44,403,500. Okay, true is always to the left. Okay, so if this statement is true, the stock goes up every time, right? So that's the other thing about decision trees and these classification models. You may run them, and you may end up with no decision tree, and that's okay because what that says about the data is there is no situation that happens every time. And that by itself is a result, right? If we had run this and they could not find something, if the machine could not have discerned that non-controlling interest was a predictor, and it worked every time that non-controlling interest is beyond 44,403,500, this thing goes up. And every time it doesn't, we then have to look at current assets, right? If this was not the case and there was nothing, that is a real result. It just means that there is chaos within the data, right? or the field that you are trying to predict is unpredictable. There may be another field, right? But this field right here does not have a rule that works or set of rules that work every time. Decision trees work every time, 100 on 100, right? Okay, so if non-controlling interest is greater than this number, okay, then it depends on what happens with current assets. Okay, I'm going to try to read that, right? So that is 2 billion, I'm just going to say 2.7 billion, right? So if the current assets are less than 2.7 billion, all right, the stock goes up. Okay, and if the current assets are greater than that, then the stock goes down. Now, this is an extraordinarily simplified model, but anybody have an intuitive reason why this may be the case? Bonus points. Bonus points if you surmise something. Yeah. So, only in the interest of time, it could be that this is because the company was smaller, right? So if current assets is less, that means you're smaller, and that means you might have been in growth mode, right? And if non-controlling interest is in fact stock, and it was less than something, that means that you were, a smaller company, right? Possibly a smaller company. So it could have been that while Tesla was in a smaller company, every time it reported, it went up, right? And as it grew, it did not, at least for the next day, right? So, okay, so that's an example of using a big data framework like VADSTI to make a simple prediction using a classification model of a decision tree on whether or not a stock will go up, specifically Tesla. Any questions?
I had a question about the Gini code, that GINI. Could you explain that a little bit, please? And just the number of samples, how did that number emerge?
Yes. Okay. So what happens is, good. So first, the Gini entropy. Okay. Gini entropy is measured as the disorder within the data set, right? And so a data set that is completely consistent, right, will have a Gini entropy of of zero. So an example of that is it's raining. If you go outside, you're going to get wet. That is like the case all the time. Like the rain is going to hit you, okay? So in that situation, Gini is zero, right? But let's say that, we have a situation here where there's an independent variable that is not always the case of the dependent variable. So when they say where there's smoke, there's fire, okay? But actually that's not correct, because you could have smoke from liquid ice, right? So there could be this, when there's smoke, there's liquid ice, right? So in that situation, the Gini of where there's smoke is not zero. It's not completely consistent, right? It's not 100% of the time. So what they're telling you up here is, at this moment, right, the Gini of non-controlling interest is only 0.48, right? So it is not a perfect predictor. In fact, it's nearly 50%. It's slightly better than 50% accurate in its prediction, right? But when you combine that with current assets, right, then it becomes 100%, right? The combination of this, right, and this always yields this, right? Because, see, non-controlling interest, if it's less than this, we could always say it's 1. That is the case, right? Win, lose, or draw, kind of. That is the situation. But we could not say the same thing when it was greater than that number. There was inconsistency, right? And that inconsistency is represented by this Gini number. You see? Okay. And so as you go down the tree, you'll notice this Gini number starts to, drop, right? And this is the composite disorder that we have at this point, right? And so we went from up here to 0.48 to now 0.44, okay? And so now what's happening is it's saying, okay, so, you know, there's some disorder at this point as well, right? But we can clearly say if it goes this way or that way, this is the prediction. And so it's not that current assets is, so if current assets is always something, then we have it, right? But and you couldn't use current assets by itself, because if current assets by itself was 0, it would be up here, right? So the combination of these two is what yields this Gini number, right? And we'll get into the internals of this tomorrow. So we can calculate that, and you actually step through each of these columns and you say, how much less consistent and inconsistent are you, right? That's effectively where Gini comes from. 5 of these points equal these points exactly, Gini is 0. There's no disorder in that data set, totally consistent, right? But let's say 3 of the points and 3 of the points, 3 of the, like when you have yes, it equals 1. And the other 3 points you have yes, and it equals 0, right? So now you can't say what yes means at all, because half the time it said 1, half the time it said 0. That Gini entropy is 1. Complete disorder, right? So that's where these numbers come from. And I'll walk you through how we page through it. Okay, now the samples, right? So in the beginning you had 5 samples, right? And what this is telling you is you had 2 that were 1s, right? And you had 3 that were 0s, okay? Or yeah, 2, at this point you have 2 and 3, right? That are leaning which way. So there's 2 that appear to be 1s, and there's 2 that appear to be 0s here, or 3 that appear to be 0s here, okay? And the color, right, is saying that it's actually the other way around. I think you have 3 1s. Let me make sure this is right. Let's go back to the labels to be sure. Yeah, you have 3 1s, okay. So this is the amount of 0s you have, and this is the amount of 1s you have. So downs and up, okay? And the predominant class here is the up, which is why it's blue, right? So this is clear. There's no doubt in the value, which is why it's full blue over here, okay? And up here, you had more ups than downs. But as you split, 2 of them went this way, okay? So 2 of these 3 went down over here, okay? And now you're left with the 2 that were 0, so went down, okay? And the 1 remaining up, right? So at this point, you've gotten 2 of them have been classified, right? So of the data set, we had 5 points. 2 of them went to the left. Those are the 1s, okay? You now have 2 downs and 1 up left, right? And because there is more of a closer difference, like 1 versus 2 and versus 2 versus 3, this is closer. That's why you get that beigeish color, right? It's a little bit, closer here, okay? And so then what happens is this 1 comes down here, right? So you have 0 downs and 1 up, right? And those 2 come down here. So you have the 2 downs and 0 ups, and they are a part of the class down, right? So that's how it splits itself. So there's 2 down here. They are both down, right? And that's, there's 2 classes. So sklearn by default takes blue and like this orange, right, for contrast. And so, yes, that's how it's walked and it splits. Yeah. Answers your question?
Yes, thank you. I have
Yeah,
noise in the
yeah.
background, so I'm keeping it on mute.
Yeah. And so we can get into the internals of how all this happens. It's actually quite interesting. And so let me leave you all with a question, okay? And it'll become more obvious when we go through the internals of how this thing works. So a decision tree looks at patterns, right? It looks at, okay, when it was, such and such value, it was 0, and so is that consistent? Is every time it is this value, is it mapped to something, right? Very much like that episode where we had the example we had of the restaurant, right? So if you look at, we did quite a bit of annotating here. So if you look at this, right, this is concrete, right? Like every time the food, you can look at this, and so let's just walk through it real fast. Every time the food is great, so you had great 1, great 0, inconsistency, okay? So, but we keep going, all right? Great 1, great 1, great 1, great 1, great 1. So yes, there was an inconsistency, but it was pretty darn close, right? And if you consider that versus the other columns, so let's just do speedy, right? So Y1, Y1, Y0, inconsistency, Y0, inconsistency. Total disorder at this point because you have 2 1s and 2 0s, right? So you can't really say anything about when the service is, but when it's speedy by itself, because you had 2 times that the guy got tipped and you had 2 times that the person did not get tipped, right? So you can't say anything at this point. And then another one for 1, another one for 1, another for 0, another for 1. So there's more disorder, more entropy in that column, right? And so what we do, right, and it's really quite magical. It's probably how you would think about it if you were trying to figure out how to do this through analysis manually. You'd look at these variables and say, all right, well, let's just look at this variable, right? And I'm going to look at what happens when it's good. And then I want to see what happens when it's, the service is good as well. We'd sort of select down in Excel, like give me all the goods and then give me all the, the service is speedy or the service is not speedy, right? And you would end up with something similar to this tree. You'd end up with, here are the goods and there's one inconsistency, but here are the, G and Y is 1, right? G and Y is 1. So these combinations are more accurate, right? So let's just see that. So you saw individually it didn't work, right? But GY is 1, GY is 1, GY is 1, GY is 1. You see that? So that by itself is perfect. And look what it says, GY, yes. You see that? So you go through, and that's what the decision tree does. It considers all combinations, and it looks for the consistencies, right? And those combinations that have low consistency, and it does it across all variables, right? This is beyond human capability now. This is with 3 columns, with only 3 values, I think, at max. But imagine you had 30 columns and 100 values, okay? So that's kind of how this works. Now, these are categories. So here's my question to the class, okay? These are categories, and we can map perfectly from the categories. What do you think happens when the independent variable is a number? I'll leave you with that, and we will come back and talk about what happens tomorrow with that case. Yeah. Okay, any questions? Yeah. William, I think you're muted. Still muted. I think, yeah, I still can't hear you. Kenneth, can you say something? Let me just make sure my speakers aren't out.
Yes,
Yeah.
I can hear you. Yes.
Okay, I got Kenneth. William, you're not coming through for some reason. Yeah.
Well, thank you for the presentation while I'm unmuted.
Oh, yeah. Good. Yeah. Sorry, William.
You're still mute.
I think he shows up as being muted in the WebEx.
Yeah, really, maybe put the question in the chat area.
Yeah, that's good. Sorry, John, go ahead. Let me see, where is the...
William, just go back and come back in. Go out and come back in. That'll be easier.
Yeah, it looks like he's okay. While that's happening, does anybody else have anything they'd like to ask? Yeah. William, tomorrow. Sure, William. Yeah. Yeah.
So any further questions for Professor Saga? Okay, so if you don't have any further questions, then we'll see you all again tomorrow, same time. And then as usual, Professor Saga, we thank you for an excellent, very informative presentation. So we'll see you.
I'm sorry, do you have the slides? Are you going to send the slides to us?
Yes, I'll set the slides out. Yeah, so I'll send the
Okay.
slides out and I'll post the notebooks and the files. Yes, and tomorrow we'll look at some of the internals and I'll show you how this stuff works in Spark as well.
All right, thank you.
Okay. Question. One question. You left us with what happens when the independent value is a number. Is that correct?
That's right.
Okay.
Yeah. That is like yes. I'm very curious to see what you all come up with, right? So,
Great.
Yeah.
Okay. Thank you.
You're welcome. Mm-hmm.
Thank you for today's lecture.
Mm-hmm.
Hello, Prem.
You're welcome.
Yeah. Hello, Prem. Yeah, just a quick. I know we're out of time, but I think I like today's lecture a lot. And then definitely all the other lectures. I think what I would like to just for TA sessioning is being able to explain well the DASC data table, PySpark. So one is just the parallel computing libraries, right? So we have the parallel computing libraries, and then we do have the in-memory heavy-duty architecture, which is a Spark. Now, if you don't have the knowledge to set these up, then of course you go with the one that already comes default with Python, which is the DASC and maybe data table, right? Is that the notion of this high performance big data analytics tools that are available in Python?
Yeah. So William, you went out for a little bit, but I think are you basically asking like when you use Spark versus DASC?
Yes. So primarily, yeah. So I have Spark, which is the ultimate PySpark with a Spark back end, and then I have DASC, which is a bunch of libraries to help mimic in-memory processing. But actually, what you are doing is you are doing parallel computing, right? You are using the library, right? So then, where does the power of big memory? I mean, why would you use DASC instead of PySpark if ability to understand is not an issue, right? So because one is just chopping the data up, and one is actually giving you access to all the data in memory, and so there's going to be a speed and there's going to be a scalability issues.
Yeah. So what's happened is, so DASC has come a long way, right? So it started as just a graph engine with delay processing, right? And it was built to work on arrays, gigantic arrays in parallel, scientific computing, right? And it came out of, it was engineered largely at NVIDIA, and it was mostly for that. And then what happened is they said we can use the same attacks on Pandas data frames. And so now the shuffling and the memory management rivals what you have in Spark, right? So they're very competitive now, but there are some differences, right? So practically, what it comes down to is Spark SQL. And Spark, okay, and in fairness, Spark does some things that DASC cannot do. So if you needed like Spark streaming, right, that is an offshoot that DASC has no parallel for right now. And so what Spark streaming is basically, you're in a car and the machine is reading in real-time data and having to do some feature engineering and some machine learning on that data, and the data is gigantic, big and fast, big problem, okay? So if you have that scenario, then you need something that is able to work horizontally and avoids dealing with the oil can of atomic data, right? And Spark has APIs built for that. DAST does not. You'd have to sort of write that, right? But, and one other thing, Spark SQL, and you'll see this tomorrow, Spark SQL gives you the ability to write joins just like SQL. So let's say you're an organization that is getting ready to modernize and you want to start doing big data and machine learning, okay? And you have SQL databases all over the place, right? And you have hundreds of pages of SQL, okay? Rather than getting rid of all of that and porting to Python with merge operations, you can take all that SQL and just put it into Spark data frames, right? So you and let me tell you, some of you may not have seen scary SQL. I have seen SQL that will turn your head around, right? Like I've seen pages and pages of SQL, notoriously difficult to debug, right? So, you know, yes, we'd like to get rid of it, but if it works and there's some queries that are unbelievably challenging, you can use all of that inside of Spark straight away, right? So, and we'll do that. Tomorrow, you're going to see the exact same model, but you'll see it built with Spark SQL. So the big advantage is Spark. SQL reuse, SQL language reuse as well. And then the ability to use some of the more advanced libraries like Spark Streaming, okay? Now, that being said, right, DAST is so much simpler to install. The learning curve to getting Spark going is enough to dissuade people, right? And so, and if you are a newer shop where you're not worried about porting all the SQL and you've got a Python workforce, that's the other thing, DAST is for Python, period. Spark works for R, Python, Java, Scala, whatever, right? But if you're a Python shop, and a lot of shops are, right? And you're not worried about porting SQL and you want something simple, DAST can do it, right? So my recommendation is, I cannot believe I'm going to say this. My recommendation for newer shops is DAST. Yeah. And that is because it's just so much simpler. So much simpler, yeah. And they've come a long way. Like Dask is backed by, you know, pandas, and Dask are the same thing, right? So, and the thing is, do you really want, you know, data scientists are not usually big data engineers, and they're definitely not sysadmins, okay? So do you want them setting up these clusters? Like you want it to be as easy as possible. So, yeah, but great question. Oftentimes you see both. I am steering our organization towards Dask. Yeah.
Okay, thanks a lot. Thank you. And then tomorrow we'll talk about data frames, I'm sure. But I think we've run out of time, so thanks a lot. Just for TA session, right? Just for TA session. Yeah. Thanks.
Anything else? Everybody stay safe. I saw the Johnson & Johnson news. Good Lord. Right? Yeah.
Yeah.
We still don't have it. Has Howard gotten it? We still don't have it. Yeah. Yeah, I don't know. We're all anxiously trying to vaccinate. Listen, something we'll talk about tomorrow is, and I'm still putting the numbers together, but I believe that Pfizer is superior to Moderna. And I'm looking at the CDC data to validate that. So if you've already got Moderna, okay,
really?
Yes.
Oh, I didn't know that.
And you know what's funny is it's real fast. So you're free to go, right? This is me just bantering now, okay? So if you look at the CDC site for the safety of these vaccines, right? You'll see that they publish Johnson & Johnson. They got to take down, right? But they publish Moderna and Pfizer, and they talk about in the Pfizer description. They say there have been some deaths associated, right? But they do not say that for Moderna. Okay, so a layman will look at that and say, "Oh, Moderna must be safe." Guess what? If you go to the CDC's Wonder database, okay, I will take you there tomorrow. All right. If you go, you can do it now as well as you wish, but it takes like a dissertation to figure out how the CDC databases work. All right. So sorry, CDC employees, Wonder needs help. Okay. So if you go to the CDC database and you look at Wonder and you look at vaccine deaths, okay, I've isolated down the query. You will see that Moderna has just since January about 1,000 deaths, close to 1,100 deaths, and Pfizer has around 900. Right, but Pfizer has been administered at least 3 to 5 times more, right? So the chance of death is low in either situation, okay? But Pfizer appears to be much better. And I think I don't think it's right that they did not talk about Moderna deaths on the CDC website. Something to think about.
Is it death after the first dose or the second dose?
They have both.
Death is death.
Death is death. I mean, hold on, Hannah. So you've asked something interesting. Let me move the screen so you can see it. So I'll read you one of them, right? So where is it? Here, and then I think I have it. 30 seconds on this one. Okay, CDC. Is this it? I think this is it. Did I make it large? My session may have timed out. Let's try this again. Okay, yeah, so let me close this. And I don't know why it's small. Oh, it's refreshing. But, they have the place that they died, the manufacturer, and then they tell you, like, patient tested positive for COVID-19, patient was very ill, number of patients already tested for vaccinated, continue an effort to prevent this patient from contracting the virus and mitigate risk. Unsuccessful patient died. Like, they have like this data here, right? And so this is an example where they already had it, but okay, I have to run the queries again, right? And we'll go through it more tomorrow. But some people die after the first shot, Nana. Some people die after the second shot. I have to look more in detail, but they have all of that. Now, I'm not saying, listen, I'm going to do some data science. I'm not saying don't vaccinate, okay? Because it looks like it's interesting, and we'll go through the data tomorrow. There's 10,000 some odd deaths since the trial started, right? So, yes, 10,000 people have been given and people don't know that, but 10,000 people have been given the vaccine and died. They have attributed it to the vaccine, okay? But the reality is some 66 million people have been vaccinated. So the probability of you dying from the vaccine is, in general, low, right? But what we don't know, Nana, is if you happen to have this allergy and you happen to be in this age group and this gender and maybe in this state, are the chances much higher that you die, right? And are you better off going to Moderna or Pfizer, depending on these little features, right? So, that is some of the stuff that I'm looking at, and we can get into tomorrow because I'm fascinated by that because, I don't know, I want to know. I personally am going to try for Pfizer, right? But let's see.
Hi, I just wanted to say something I would like to know as well because I've already had my first shot with Moderna.
Yeah.
I'm okay. My neighbor, she got a little sick, but she's okay. I don't know if the reason they're not telling people about the deaths is because they want to quickly get people vaccinated. That's what I'm thinking. But that's very important to know because you may have an allergy or, whatever, because it could have been a preconditioned situation with the people who died. So we don't know for sure.
That is exactly right. And I can tell you that they've not crunched it, and we should crunch it. So here, I'm going to try to do this again. Let's see. So we have it, and we have the allergy information. So let's just punch this.
None of them are afraid.
I read last week from somewhere that your one's blood group could also impact on the adverse effect that one could have.
Yeah. And so we need to know, like they should specify if you have these type of conditions or, you fall into these independent variables, don't take it, right? Or take a certain vaccine because they're different. And, let's see. So we have, there is the allergy data as well. They have that in here, history and allergies, right? So, we can find if you have certain allergies, these are the people who passed. Now, the problem is the CDC only gives you 10,000 records. So you have to run this query a couple of times to put it together, right? But the data is here. And so, what happens if we find, this is just me kind of guessing, but what happens if you find that people with more than one allergy are that much more likely to die from this, right? Even if the allergies aren't listed in the drug. And that comes into play because if you're otherwise healthy, then you're in an age group that's not at high risk, you are most likely going to beat COVID. So now you have to ask, is the risk of the vaccine because of these allergies I may have higher than me beating the actual, virus, right? So I don't know. I'm going to try to find out because I have to take this vaccine at some point, and I want to know what it is, right? So, yeah, I don't know. More on this tomorrow, but if you're curious, as a second homework problem, go to the CDC. It's Wonder, okay? And please, this is me horizontally scaling the effort, okay? If you are bored and you want to help figure out what is going on, right, go to the CDC website, and here, I will post this in the chat. So wonder.cdc, and you can search for, let me show you the terms. It's the request form, and the thing, they don't tell you this, right? You have to kind of figure it out. You have to set the VAERS ID as the first field, okay? So everything is group bys here, right? And then you can group by whatever you want here, and you can add these. And then you can add in COVID-19 as the vaccine, and I filtered it down by death, life-threatening, permanent disability, and birth defects. All right, the last thing you'll need to know is they don't bring back more than 10,000 records, so you'll have to filter it by time, and that is down here. Everybody who died after January 2021. There's 2,000 some odd people that have died after January. There's about 10,000 people that have died in total, and that's because they died in the trial. So, yeah, let me post this in the...
Then why are they making noise about the J&J death if this already existed?
This already existed? So, I think it goes back to what one of the members in the group said is it has to be like there's damage control, Nana. Right? So, it just comes down to, if they come out and two things on this. First, it could have been that Johnson & Johnson had really egregious results for blood clots, so they had to pause it, okay? Right, so maybe the data was just bad and they saw it, okay? Magically, right? The second side of this is maybe it's bad kind of all over the place, but Johnson & Johnson has not rolled out as much, Nana, right? Let's take another view of this. I think 40, 50 million people have gotten Pfizer. What happens if you say Pfizer is causing blood clots and you pull it, and the vast majority of people that got vaccinated have taken Pfizer? Right? The distrust that would be involved would be massive, right? People would be like, what is this, right? So I don't know, Nana. These are just possibilities, right? I can tell you that if you go to the CDC, let's go to the CDC website. All right, so if you go to the CDC website, COVID vaccine safety, right? They make no mention of these deaths, right? So safety of COVID-19. Let's go to Moderna real fast, okay? See if they updated it, but I don't think they have. Actually, let's move this. All right, and so Janssen & Janssen, right? So they paused this, but if you go to Where's Moderna? Vaccines. Here, this is the homepage for it. Let's do this. Find a vaccine. Johnson & Johnson, update. Hold on, let me search for Moderna. They should be publishing this, and I did not see it, so let's be sure. Okay, here we go. Okay, who should get it, who should not get it? Okay. So yes, if you have an allergic reaction to that. But do they talk about deaths anywhere? No. Right? One of the side effects is also death. I'm here to tell you. Okay, I can assure you, you just saw the death record, right? So it's not talked about here anywhere, right? Okay. But if you look at Pfizer, look at Pfizer real fast. Okay. They haven't put it out here. They had it in here before where they said that Pfizer had some deaths. Let's see. No side effects, a small number. There we go. Done. Bang. Okay. All right. So Pfizer, they point out that there were deaths. Right. Let's go back and let's see if they've updated that for Moderna. It is here. Okay. Let's go back to Moderna. This is the last thing now. Let's see if they got it. Nothing. But you and I know that Moderna has more deaths than Pfizer. Okay? So it gets more interesting. Like, it may be, why are certain areas getting more Moderna than Pfizer? Like, I'm highly suspicious of things. Okay? I'm not saying don't vaccinate. I'm just saying that I'm surprised that things are not being reported. All right? So, okay. Anybody else got anything? All right.
Well, it's important to know that Pfizer also made Viagra, you know. So
Oh, I didn't hear it. Yeah.
they can raise the dead. If they can raise the dead, they
data for
can
that.
cure the virus.
Okay. That being said, have fun with the CDC database. See what you can find if you want. Definitely think about numerics, and then we'll get into this. I'll see you all at 11. If you need to reach me, prem@umd.edu. Let me put this in the chat. So if you need me for any reason, Nana, I'll move all the stuff in as well. And everybody stay safe. Huh?
All right. Thank you so much.
You're welcome. Okay. Okay, see you guys.
Yeah, thanks so much.
You're welcome. Thanks, guys. Bye.
Hey, be careful.